What is a supercapacitor and how does it work? Supercapacitors, also known as ultracapacitors or double-layer capacitors, are energy storage devices that bridge the gap between traditional capacitors and batteries. They have unique properties that make them suitable for specific applications that require high power density and rapid charge/discharge cycles. Here are some key points about supercapacitors. Electrostatic energy storage is a method of storing electrical energy in a capacitor using the principle of electrostatics. It involves the accumulation of electric charge on the electrodes of a capacitor, creating an electric field between them. This electric field stores energy in the form of electrostatic potential energy. The key aspects of electrostatic energy storage in capacitors are as follows. Electrostatic charging: when a voltage is applied across the terminals of a capacitor, electric charge accumulates on the surfaces of the capacitor's electrodes. Positive charge builds up on one electrode, while an equal and opposite negative charge accumulates on the other electrode. This process creates an electric field between the charged electrodes. Energy storage mechanism: the electric field between the charged electrodes stores energy in the form of electrostatic potential energy. The energy stored in the capacitor is proportional to the square of the voltage, V, applied across the capacitor and the capacitance, C, of the capacitor, given by the equation, energy, E, equals 0.5 *C *V squared. Dielectric material: the dielectric material between the capacitor's electrodes plays a critical role in electrostatic energy storage. The dielectric material acts as an insulator, preventing direct electrical contact between the charged electrodes while allowing the electric field to exist. Capacitance: capacitance is a fundamental property of a capacitor that determines its ability to store charge and energy. Capacitance is defined as the ratio of the stored charge, Q, to the applied voltage, V, given by the equation, C equals Q/V. Capacitance is usually measured in farads, F, where 1 farad is equivalent to 1 coulomb of charge stored per volt of applied voltage. High power density: capacitors, including supercapacitors, are known for their high power density due to their ability to charge and discharge rapidly. The electrostatic energy storage mechanism allows for efficient charge and discharge cycles, making capacitors suitable for applications requiring high power delivery. Low energy density: while capacitors exhibit high power density, their energy density, energy stored per unit volume or mass, is lower than that of batteries. This limitation makes capacitors more suitable for applications that require rapid energy delivery rather than long-term energy storage. Electrostatic energy storage is a fundamental principle that underpins the operation of all capacitors, ranging from traditional capacitors with dielectric materials to supercapacitors using double-layer capacitance and pseudocapacitance for enhanced energy storage. The ability to store and release electrical energy quickly and efficiently makes capacitors indispensable in various electronic and electrical applications, from smoothing power supplies to providing instantaneous power in high-power systems. High power density in the context of capacitors refers to their ability to deliver or absorb a large amount of electrical power relative to their physical size or weight. It is a measure of how quickly a capacitor can charge or discharge and is an essential characteristic in applications that require rapid energy delivery or absorption. Here are some key points about high power density in capacitors. Definition: power density is defined as the amount of electrical power that can be delivered or absorbed by a capacitor per unit volume or mass. It is typically expressed in watts per cubic centimeter, W/cm superscript 3, or watts per kilogram, W/kg. Rapid charge and discharge: capacitors with high power density can charge and discharge rapidly due to their low internal resistance, ESR, and other design features. They can rapidly store and release electrical energy, making them suitable for applications requiring quick energy transfers. Pulse power applications: high power density capacitors are used in pulse power applications, where rapid and high energy pulses are required. Examples include electromagnetic pulse (EMP) generators, pulse-forming networks (PFN) in pulsed power systems, and laser power supplies. Regenerative braking. In electric and hybrid vehicles, high-power density capacitors, such as supercapacitors, are used in regenerative braking systems. These capacitors quickly absorb the energy generated during braking and store it for later use, increasing the vehicle's overall energy efficiency. Flash units and cameras. In photography, high-power density capacitors are used in electronic flash units to provide the intense burst of light needed for capturing images. Capacitors rapidly charge and discharge to produce the bright flash. Power inverters and converters. High-power density capacitors are employed in power inverters and converters to store and release electrical energy during the conversion process. They contribute to efficient energy conversion and reduce power losses. Burst power requirements. Applications that have peak or burst power requirements, such as pulsed radar systems, communication equipment, and aerospace systems, benefit from high power density capacitors that can quickly respond to sudden power demands. Supercapacitors, also known as ultracapacitors, are known for their high power density compared to traditional capacitors. They can deliver and absorb high power levels due to their unique electrostatic energy storage mechanism and electrode materials. Energy storage and backup. High power density capacitors are used in energy storage and backup applications, where quick charge and discharge cycles are essential. They can act as efficient buffers to provide rapid power when needed. Portable electronics. Capacitors with high power density are used in portable electronic devices, such as smartphones and tablets, to deliver bursts of power during high energy demand operations. High power density capacitors play a vital role in various industries and technologies where quick energy transfer and rapid charge/discharge cycles are critical. They provide efficient energy storage and delivery solutions in applications ranging from automotive systems and aerospace technology to consumer electronics and industrial equipment. Rapid charge and discharge refer to the ability of a capacitor to quickly store and release electrical energy. Capacitors with rapid charge and discharge capabilities are capable of efficiently absorbing or delivering energy in a short amount of time. Here are some key points about rapid charge and discharge in capacitors. Low equivalent series resistance (ESR) capacitors with low ESR can charge and discharge more quickly. ESR is the sum of all internal resistances in a capacitor, including resistance from the dielectric material and the electrode connections. Low ESR reduces power losses and allows for faster energy transfer. Low internal inductance (ESL) inductance in a capacitor, also known as ESL, equivalent series inductance, can limit the rate of charge and discharge. Capacitors designed with low ESL have reduced inductive effects, enabling faster charge and discharge cycles. Energy storage mechanism. The mechanism of energy storage in a capacitor plays a role in rapid charge and discharge. For example, supercapacitors store energy through electrostatic charge accumulation, which allows for faster energy transfer compared to traditional capacitors that rely on dielectric polarization. High power density. Capacitors with high power density are designed to handle high power levels and can quickly absorb or deliver energy. They are engineered to have low ESR and ESL, which facilitates rapid charge and discharge cycles. Applications. Capacitors with rapid charge and discharge capabilities are used in various applications where quick energy transfer is essential. Examples include flash photography, regenerative braking systems in electric vehicles, pulsed power systems, power inverters, and power supply applications. Supercapacitors, also known as ultracapacitors, are well known for their rapid charge and discharge characteristics. Their unique electrostatic energy storage mechanism allows for very fast charging and discharging, making them ideal for applications requiring high power bursts. Frequency response. The rapid charge and discharge capability of capacitors makes them suitable for high-frequency applications. They can effectively handle AC signals and provide energy storage and release in high-frequency circuits. Energy efficiency. Capacitors with rapid charge and discharge properties contribute to increased energy efficiency in various systems. They can quickly respond to changes in power demand, reducing energy wastage and enhancing system performance. Power electronics. In power electronics applications, such as motor drives and power inverters, capacitors with rapid charge and discharge capabilities are used to handle rapid changes in power requirements. Rapid charge and discharge are critical in applications that demand quick energy delivery, high power density, and efficient energy transfer. When selecting capacitors for such applications, it is essential to consider the capacitance value, voltage rating, ESR, and ESL to ensure that the chosen capacitors meet the rapid charge and discharge requirements of the specific application. Long cycle life in capacitors refers to their ability to endure a large number of charge and discharge cycles over an extended period without significant degradation in performance. Capacitors with long cycle life can withstand repeated charging and discharging without a substantial decrease in capacitance, voltage rating, or other critical electrical characteristics. Here are some key points about long cycle life in capacitors. Durability. Capacitors with long cycle life are designed to be durable and reliable, capable of enduring a high number of charge and discharge cycles without premature failure. Material selection. The choice of materials in the capacitor's construction, including the dielectric material and electrode materials, plays a vital role in determining its cycle life. High-quality materials that exhibit low wear and chemical stability contribute to extended cycle life. Stress and aging. Factors such as voltage stress, temperature, and other environmental conditions can affect a capacitor's aging and cycle life. Capacitors designed for long cycle life are often built to handle the stresses associated with their intended applications. Aging mechanisms. Various aging mechanisms can impact a capacitor's cycle life, including mechanical stress, chemical reactions, and changes in the dielectric material. Capacitors designed with materials and structures that minimize these aging effects tend to have longer cycle lives. Electrolyte and solid-state capacitors. Electrolytic capacitors, such as aluminum and tantalum electrolytics, can have limited cycle lives due to the nature of their electrolyte. Solid-state capacitors, including ceramic, film, and supercapacitors, ultracapacitors, often have longer cycle lives compared to electrolytic capacitors. Supercapacitors, or ultracapacitors, are known for their exceptionally long cycle life, often in the hundreds of thousands to millions of cycles. Their electrostatic energy storage mechanism and durable electrode materials contribute to their longevity. Application-specific considerations. The cycle life of a capacitor can be influenced by the specific application and the operating conditions it experiences. High-quality capacitors that are well-suited for the intended application are more likely to have long cycle lives. Quality and reliability. Capacitors from reputable manufacturers with a focus on quality control and reliability testing are more likely to provide long cycle life. Long cycle life is essential in applications where capacitors are subjected to frequent charge and discharge cycles, such as energy storage systems, regenerative braking, power electronics, and electronic devices that experience constant power fluctuations. In such applications, capacitors with long cycle life reduce the need for frequent replacements, contributing to overall system reliability and cost-effectiveness. When selecting capacitors for applications requiring long cycle life, it is crucial to consider factors such as voltage rating, capacitance stability, temperature characteristics, and reliability data provided by the manufacturer. Low energy density in capacitors refers to their limited ability to store electrical energy relative to their physical size or weight. It is a measure of how much energy a capacitor can hold per unit volume or mass. Capacitors generally have lower energy density compared to batteries, making them more suitable for applications that require quick energy delivery and high power density rather than long-term energy storage. Here are some key points about low energy density in capacitors. Energy storage mechanism. Capacitors store energy through electrostatic charge accumulation on their electrodes. The energy stored is proportional to the square of the voltage, V, applied across the capacitor and the capacitance, C, of the capacitor, given by the equation, energy, E, equals 0.5 C V squared. High power density. While capacitors have low energy density, they typically have high power density. Power density refers to their ability to deliver or absorb power quickly, making them suitable for applications that require rapid charge and discharge cycles. Complementing batteries, capacitors are often used in conjunction with batteries in electrical systems. While batteries provide high energy density for long-term energy storage, capacitors provide quick energy delivery and short-term power bursts. Supercapacitors, also known as ultracapacitors, have higher energy density compared to traditional capacitors. While their energy density is still lower than batteries, their unique energy storage mechanism allows for higher energy storage capacity than regular capacitors. Pulsed power applications, capacitors with low energy density are commonly used in applications that require short bursts of high power, such as pulsed power systems, laser power supplies, and electromagnetic pulse (EMP) generators. Limitations in energy storage. The primary limitation of capacitors' energy storage capability is the absence of a chemical reaction-based energy storage mechanism, which is found in batteries. Chemical reactions in batteries allow for higher energy density but typically at the expense of slower charge and discharge rates. Energy efficiency. While capacitors have lower energy density, they are highly efficient in rapidly delivering stored energy without significant energy losses during charge and discharge cycles. Size and weight considerations. Capacitors with lower energy density can be physically larger or heavier compared to batteries for the same energy storage capacity. Overall, capacitors with low energy density are favored in applications that require high power density, quick response times, and efficient energy transfer. They excel in situations where energy needs to be delivered rapidly, such as in pulse power systems, regenerative braking, power electronics, and applications requiring rapid charging and discharging. However, for applications requiring long-term energy storage, batteries with higher energy density are typically preferred. The choice between capacitors and batteries depends on the specific energy requirements and performance characteristics of the application. Capacitors are often used as complementary components to batteries in various electrical and electronic systems. Both capacitors and batteries serve different functions, and their combination provides a more efficient and reliable energy management solution. Here are some ways in which capacitors complement batteries. Power delivery and surge protection. Capacitors have high power density and low internal resistance, allowing them to deliver or absorb electrical energy rapidly. They are used to supplement batteries in applications where a quick burst of power is required, such as starting motors, providing peak power for electronics, and compensating for sudden surges in power demand. Energy buffering. Capacitors act as energy buffers in conjunction with batteries. They store energy during periods of low power demand and release it during high power demand situations. This helps to stabilize voltage levels and reduces the stress on the battery by handling sudden changes in energy requirements. Power quality and stability. Capacitors can improve power quality by filtering out noise, reducing voltage fluctuations, and smoothing the output voltage from batteries. This ensures a stable and consistent power supply to sensitive electronic devices. Quick charge and discharge. Capacitors can be rapidly charged and discharged, allowing them to provide near-instantaneous power when needed. In contrast, batteries may have slower charge and discharge rates due to their chemical energy storage mechanism. Energy efficiency. By using capacitors to handle short-duration, high-power bursts, the overall energy efficiency of the system can be improved. Capacitors can handle frequent charge and discharge cycles efficiently, reducing energy losses during rapid power transfers. Regenerative braking. In hybrid and electric vehicles, capacitors are used in regenerative braking systems to capture and store energy during braking. The stored energy can then be quickly released to provide additional power during acceleration, reducing the load on the battery and improving overall energy efficiency. Voltage regulation. Capacitors assist in voltage regulation in power supply circuits. They help smooth the output voltage and compensate for voltage drops, ensuring a stable power supply to connected devices. Backup power. Capacitors can act as quick backup power sources when the primary power source, such as a battery, fails or is disconnected. They provide temporary power to critical systems during the switchover or emergency situations. By combining capacitors and batteries in a system, designers can take advantage of the strengths of both components to optimize energy storage, power delivery, and overall system performance. This complementary approach helps create more efficient and reliable systems in a wide range of applications, from consumer electronics to industrial power management and renewable energy systems. Supercapacitors, also known as ultracapacitors or double-layer capacitors, come in different types based on their energy storage mechanisms and construction. The main types of supercapacitors are as follows. Electric double-layer capacitors, EDLCs, are the most common type of supercapacitors. They store electrical energy through the electrostatic charge accumulation at the interface between the electrode and the electrolyte. The electrodes are typically made of high surface area activated carbon or other conductive materials. EDLCs offer high power density and rapid charge and discharge capabilities, making them suitable for applications that require quick energy delivery. However, their energy density is lower than some other energy storage technologies. Pseudocapacitors are a subclass of supercapacitors that store energy through both electrostatic charge accumulation and fast, reversible Faradaic redox reactions at the electrode surface. This combination of double-layer capacitance and pseudocapacitance results in higher energy density compared to EDLCs. Pseudocapacitors often use transition metal oxides or conducting polymers as the electrode material. They offer improved energy storage capability while still maintaining rapid charge and discharge characteristics. Hybrid supercapacitors combine the benefits of both EDLCs and pseudocapacitors. They use a combination of carbon-based electrodes for double-layer capacitance and a redox-active material for pseudocapacitance. Hybrid supercapacitors aim to achieve a balance between high energy density and high power density, making them suitable for a wider range of applications. Asymmetric supercapacitors are constructed using different materials for each electrode, resulting in an asymmetric charge storage mechanism. One electrode is designed to have a higher capacitance, double-layer capacitance or pseudocapacitance, than the other, allowing asymmetric supercapacitors to achieve higher energy density than conventional symmetric supercapacitors. Solid-state supercapacitors. Traditional supercapacitors use liquid electrolytes, which can sometimes limit their operating temperature range and lead to potential leakage or safety concerns. Solid-state supercapacitors, on the other hand, use solid-state electrolytes, which offer improved safety and thermal stability. These supercapacitors are still under development and have the potential to provide enhanced performance and safety in various applications. Each type of supercapacitor has its unique characteristics, including energy density, power density, and other performance parameters. The choice of supercapacitor type depends on the specific requirements of the application, such as the need for high power delivery, high energy storage capacity, or a balance between the two. As supercapacitor technology continues to advance, they are finding increasing use in various applications, including renewable energy systems, electric vehicles, regenerative braking, power backup systems, and electronic devices requiring quick energy delivery. Applications. Supercapacitors, with their unique characteristics of high power density and rapid charge/discharge capabilities, find applications in various industries and technologies. Some of the common applications of supercapacitors include electric and hybrid vehicles. Supercapacitors are used in electric and hybrid vehicles to provide quick bursts of power during acceleration and regenerative braking. They complement batteries by handling high power demands, extending battery life, and improving energy efficiency. Renewable energy systems. Supercapacitors are utilized in renewable energy systems, such as solar and wind power installations, to store and release energy rapidly during fluctuations in power generation or grid demand. They help smooth out variations in energy production and improve system stability. Power backup and UPS. Supercapacitors serve as quick power backup solutions in uninterruptible power supply (UPS) systems. They can provide temporary power during short outages, allowing critical systems to continue functioning until a more extended power source, such as a generator, kicks in. Consumer electronics. Supercapacitors are used in consumer electronic devices, such as smartphones and digital cameras, to provide quick charging capabilities for flash units and other high-power components. Regenerative braking. In trains, trams, and electric vehicles, supercapacitors capture and store energy during braking, which can be used later to assist in propulsion during acceleration. Pulsed power systems. Supercapacitors are employed in various pulsed power applications, including electromagnetic pulse (EMP) generators, lasers, and pulsed radar systems. Their ability to discharge quickly is well suited for these high-power, short-duration pulse applications. Power quality and voltage stabilization. Supercapacitors can improve power quality by providing rapid voltage stabilization and short-term power support in grid applications. Peak load shaving. Supercapacitors are used in industrial applications to shave peak loads and reduce strain on the power supply during periods of high demand. Portable electronics. Supercapacitors are used in portable electronic devices to provide quick energy delivery for high-power functions like vibrating motors and LED flashes. Aerospace and defense. Supercapacitors find applications in aerospace and defense systems such as space satellites, unmanned aerial vehicles, UAVs, and defense electronics, where rapid power delivery and energy efficiency are critical. Microgrids and smart grids. Supercapacitors are integrated into microgrid and smart grid systems to enhance grid stability, support renewable energy integration, and provide grid balancing services. Industrial automation. Supercapacitors are used in automation systems to provide short-term power during power outages, enabling controlled shutdown procedures and protecting critical equipment. The application of supercapacitors is continually expanding as technology advances and new innovations are developed. Their unique properties make them valuable in scenarios that demand rapid charge and discharge capabilities, energy storage and release efficiency, and high power density in various sectors of modern technology and energy management. Carbon-based electrodes. Carbon-based electrodes are a common type of electrode used in various energy storage devices, including supercapacitors. These electrodes are made primarily from different forms of carbon materials due to their high surface area, electrical conductivity, and stability. The choice of carbon material for the electrode is crucial in determining the performance and characteristics of the supercapacitor. Some commonly used carbon-based electrode materials include activated carbon. Activated carbon is one of the most widely used materials for supercapacitor electrodes. It is a highly porous form of carbon with a large surface area, which allows for high charge storage capacity through the process of adsorption and desorption of ions at the electrode-electrolyte interface. Activated carbon can be derived from various carbon sources, including coconut shells, wood, and coal, by a process of activation that creates an extensive network of pores. Carbon nanotubes. CNT's carbon nanotubes are cylindrical structures made of carbon atoms arranged in a hexagonal lattice. They possess exceptional electrical conductivity and mechanical strength, making them attractive candidates for supercapacitor electrodes. CNTs offer high surface area and unique properties that enhance the electrochemical performance of supercapacitors. Graphene. Graphene is a single layer of carbon atoms arranged in a two-dimensional honeycomb lattice. It has excellent electrical conductivity, high surface area, and mechanical strength. Graphene-based electrodes have been extensively researched for supercapacitors due to their potential for high-performance energy storage. Carbon aerogels. Carbon aerogels are lightweight, highly porous materials made from carbon-based precursors. They have a three-dimensional network structure with an open cell architecture, providing a high surface area for charge storage. Carbon aerogels exhibit low density, high electrical conductivity, and mechanical flexibility, making them suitable for specific supercapacitor applications. Carbon nanofibers. Carbon nanofibers are carbon materials with a fibrous morphology, often resembling tiny fibers. They possess high electrical conductivity and can be tailored to have a controlled porous structure, making them suitable for use in supercapacitor electrodes. Carbon black. Carbon black is a fine powder form of carbon used as a filler material in electrode formulations. It is commonly added to enhance the electrical conductivity and mechanical properties of the electrode. Carbon-based electrodes are favored for supercapacitors due to their abundant availability, cost-effectiveness, and excellent electrochemical performance. The high surface area and electrical conductivity of these materials enable efficient charge storage and rapid charge and discharge cycles, making them well suited for high power, quick energy delivery applications. Researchers continue to explore novel carbon materials and electrode designs to further enhance the performance of supercapacitors and expand their applications in various industries. Supercapacitors have gained significant attention in recent years due to their unique capabilities, and ongoing research is exploring ways to improve their energy density and overall performance. They are particularly valuable in applications where high power demands, fast charging, and long cycle life are essential, complementing the strengths of traditional batteries in energy storage systems.